And start recording. Hello everyone! Welcome to Handmade Hero, the show we code a complete game live on stream. I don't actually remember having anything outstanding at the end of last week in some very odd turn of events that is somewhat inexplicable. Despite kind of fighting with multi-sampling and depth peeling for 2 or 3 sessions, at the last minute, MTS Mox happened to find a problem we had with our depth enable and re-enable, and we fixed it. And that kind of gave me new impetus to go look to see if we can get multi-sample depth peeling working. And I randomly tried a technique that seems to work incredibly well for us. It's splitting the depth, the total depth delta on a multi-sampled pixel. And so just to recap, I guess I'll sort of show you on the blackboard what it was, but I was not expecting this to be anything special. Looks like I gotta restart my Milton. Let's see here. Nope, not Handmade Con. That's the drive. Oh man, I don't even want to tell you. It has been a month. I found someone to do the rest of the Handmade Con videos, an editor, and I've been trying to make a hard drive with the videos on it for them to edit. And it has been seriously 4 weeks straight of me trying to get Google Drive to successfully download the files, and it has failed for 4 weeks straight. And it's been a complete nightmare. Google Drive is incredibly bad. I'm glad the only thing I've ever used it for is like basically transferring those videos. Because man, if you actually had to use Google Drive as an actual drive solution, heaven help you. Anyway, let's go ahead and restart Milton here. There we go. And we are day 389. And this is multi-sampled depth peeling. So what happened here was we were getting, we had done our depth peeling and that was great. I really liked the depth peeling. But then we wanted to try and smooth out the edges of geometry on the screen. Which we don't have much of, but we only have that one cube primitive is really the only thing I needed. The game's mostly sprites, but I wanted the ground and walls to be made up of actual geometry. And so that was still, really crispy and sparkly. It didn't look nice, right? And so we wanted something that would smooth it out. So the question was, could we get depth peeling working with multi-sampling? And the problem with that is that multi-sampling and depth peeling don't play very nicely together, since typically the way multi-sampling works is it only operates on the edges, which means that when you're filling a sprite, if you're on the interior of the sprite, right, you're just going to be filling that one pixel, essentially that one sample, and it's just going to replicate to all the samples, right? That's how multi-sampling works. If the edge of the primitives that you're working with, like let's say, this is the primitive I'm working with, this is the triangle out here. If the pixel is entirely encompassed in that primitive, multi-sampling is not active. So what it'll do is it'll just do one sample and then it'll write all the samples. It'll write to all the samples as a splat. It'll just say, reset all the samples to be this value, right? So what ends up happening is you can't really use depth peeling very effectively with this, at least not with the shader levels we're using, because you don't have any way of really taking that and doing anything with this, right? What you'd have to do is you'd have to do a for-line loop over each of the samples and effectively compare it to each sample, and you more or less would lose all of the benefits of multi-sampling. Like you might as well just start rendering at 8x the resolution, because now you're processing every sample, every pixel, every time, right? Every texel, I should say, because with overdraw. So basically, we don't really have any win from multi-sampling if we were to do that. So the question is, could we do something that worked properly with multi-sampling where instead of actually having multi-sampling persist all the way through the depth peeling process, could we do one depth peel with multi-sampling, then sort of do the resolve then to produce a regular, one sample per pixel version of that texture, pass that to the next stage of the process, and effectively just get the actual acceleration we want from multi-sampling. You know what I'm saying? And the answer seemed elusive, but then it turned out, for whatever reason, if you take a look at all of these samples and produce a min and max range, so if this was our camera looking down, and we looked at all these samples, and they kind of fell in, Z depth from the camera like this, if you take the minimum and maximum of them, and then you just split the difference, so you take half the way in between these two, that actually produces, in the vast majority of cases that I was able to find, I don't know where get my command prompt back here. Let me go ahead and run the game here so you can take a look at it. There we go. All compiled. Come on, Visual Studio, you can boot. Come on now. Oh boy. I gotta uninstall that CodeXL thing. Ever since we installed CodeXL, Visual Studio takes like years to boot. Like years. It's nuts. I don't even want to know what was going on there. All right. All right, there we go. So here you can see it running, right? And there's really no artifacts. You can get smoothing on all of the geometry, even where two pieces intersect, which we couldn't do when we were trying to do the centroid sampling version of this. But even if I switch to the debug camera and really just kind of stress it out, you don't get many artifacts. There's a couple in a few places you can see a little bit, like right in there. When you get really low to it, you can kind of see a little bit in there. But for the most part, it looks pretty good. And I'm totally willing to kind of go forward with that so far. We may have to do a little more tweaking to it later, but it's pretty good as it stands. And the only place that we really saw artifacts that we might want to try and fix at some point is here. You can kind of see when it fades in, you get a problem where the depth peel is a little too aggressive on the cubes. So you end up in a situation where you have precluded some of the depth, some of the lower stuff from showing through. So you end up with effectively like a bigger beveled edge that kind of goes through there. You can see it right along there. And that's not correct, obviously. But mostly I'm pretty happy with it. So it's a little early to declare victory, certainly, because we don't have, a full game running where we've tried all the things that, we don't know what geometry we might have in the actual game that, or sprites that might stress this harder in some way, because, since it's kind of a weird hacky technique that we just kind of came up with to solve a problem, it's hard to predict necessarily without having more experience or thinking it through a lot, trying to figure out what all the cases are where it might fail. It's hard to know if anything we might do in the future could break it in a bad way. But at the moment, I would say I'm happy, certainly happy enough with it, with the render quality we're getting here, to just go ahead and move on to something else, right? And again, that's all I did at the last minute. I was playing around with some things to see if anything would work. All I did was just take in a custom resolve pass that would split the min and the max and say that's the value to pick, and that just worked. I mean, I had a reason for doing it. It's not like it was completely blind. The idea was simply that, well, that would say that, you know, if we had samples from two different pieces of geometry, like let's say I had in here, the tree, you know, covers these samples and the ground covers these samples. My thought was, well, we want to depth peel away the tree, but we want to leave the ground in place. So if those had any substantial difference in their z at all, then picking the midway should hopefully land most of these samples on this side of it and most of these samples on that side of it. So off you go, right? And I don't, like I said, I don't really claim that that's any kind of rigorous solution to the problem, but it does seem to be surprisingly effective in a large number of cases. So yeah, that's the renderer. I guess what I would say at this point is I don't actually think we have anything in particular I want to do to the renderer now from where it is. And so one thing that I thought we might do perhaps is just say, well, you know, now that we finished all that stuff, maybe let's go ahead and just kind of add in some lighting to the renderer this weekend, because, you know, that's the one thing that we don't really have at the moment. And it looks like our image quality is good and the graphics, we accomplished what we wanted. Everything's in real 3D now. It runs through the Z buffer, so there is no sorting. You can dump as much stuff in as you want. And really the only thing that I think we might do in the future to it from the structure that's there now is when I ship the art pack to update to new artwork, I may make it so that our artwork is all kind of pre-processed to be in tiles that can all be the same resolution, roughly, so that we can use like a texture array. Because right now, you know, we on cards that aren't fast at this, on NVIDIA you don't see this at all, but we take a long time in OpenGL render commands right now, and the reason for that is we have to change texture handle every single sprite, right? Which is just way too much. A lot of modern cards can elide those changes, like NVIDIA drivers just eat those for breakfast, and that I assume is because the texture handle is just a pointer, basically. And you don't actually need to restart anything. You can just inline it in the stream, and the dispatches can just go very quickly. It's not a whole state change that happens. Whereas on old cards, that's not true. The texture unit has to be re-prepared and stuff, and it really like slows things down. So on older cards like this, you pay a huge penalty for it. On modern cards like NVIDIA, you don't even really see it. I was noticing that when I ran this on a more modern GPU the other day. So it's not super clear that that's something that we want to do for sure, but I do think it's something that we probably want to do. And when you take a look at how things are at the moment, it sure seems like that would be fine. Basically we could just have most of our stuff lives in a 256 by 256 bitmap or whatever, and off we go. And I'll just resize things to fit that properly or something. So we can do a pretty simple texture atlasing scheme, like a texture array scheme, we could do a pretty simple one of those without a lot of headache, and maybe we should, right? So we can certainly take a look at that, and so I might do something like that. But that's literally it, and all that would be is a slight change in how we're submitting our textures, and then getting that loop to not change textures every frame, every sprite. It would just change the texture once and go. So that's something we might do. Other than that, I think now we're down to optional features, right? We're getting good render quality. Everything's in 3D. I don't see sorting problems really. I don't see artifacts that I'm not willing to live with. So it's really pretty clean, and I'm willing to go forward there. So what I was thinking, is like maybe just get some basic lighting for us, because I feel like we're going to want a little bit of lighting in here. Something where we can, put down some light sources and, probably do something with some normals with the shading. We have the option of having our sprites have normal maps on them. And I don't know to what extent we really want to do that, because it's a question of whether that's going to work with the art style or not. Sometimes it can be a little bit difficult to figure out if that's going to be good or bad. But we basically have a situation where we want at least some lighting. So even if we were going to just do very basic lighting that didn't even have any normals, it was just regional, we at least want that in there somewhere, right? We want some regional lighting to exist somewhere. So what I want to do is just basically throw a little bit of that in, and get ourselves something that can have lights happen. So the way I want to do this at the moment is not particularly interesting. All I really want to do is say, well, let's go ahead and just do the simplest, stupidest possible thing, and we'll start there, right? So I'm going to go into our shaders here, and we've got this one shader that does essentially everything. So this is our compile z-bias program, right? And this is the thing that draws substantively everything. So if we put lighting into this shader in some way, everything that we drew would be lit by that algorithm, whatever it is. So what I'd like to do is start by saying, well, let's suppose that we had some light source. What could we do to put in some sort of really basic, not good, just simple lighting? So let's start with something really straightforward. Let's start with sort of a, I'll mention a few things for you. All right. So if we were going to do real lighting, there's a number of things that you have to take account of, right? And the problem with real lighting is that you kind of sometimes have to go all the way with real lighting, otherwise you're in a bit of a pickle. So first, let me say something about real lighting that's kind of difficult to understand. Trying to think of how in-depth I want to go with this, but here we go. So let's suppose that I have a source of photons, right? Because what is light? Light equals photons for our purposes. Now, I'm not trying to make a statement about quantum mechanics or anything here. So this is, graphics that we're talking about. And in terms of graphics, all we really care about in the real world most of the time is that we've got essentially light sources that emit photons from them. Those photons travel in straight lines. So when a photon is emitted from a light source, it travels in a straight line until it hits something. When it hits something, some of it, there's a percentage chance that photon will be absorbed, and there's a percentage chance that photon will be bounced out, right? And again, this is not trying to make a statement about quantum mechanics. It's just trying to make a statement about the parts we need to think about for graphics. So typically what happens is we have a light, right? And we have an eye. And what we want to know is photons that came out of the light source, they hit something, right? They bounced off and they hit our eye. We are trying to sort of say with lighting, we want to accumulate all of that, right? The ideal goal in a graphics, in a lighting algorithm, in a realistic lighting algorithm, would be to take all of the photons that were emitted over, whatever the frame time is, a 60th of a second, let's say. Take all of the photons emitted by a light source, bounce them all around, see which one of them hit the eye, and that is the lighting, right? And you can imagine this is per pixel, right? Every pixel, it's whether a photon would have come in at that point in the CCD, if it's your camera, or your retina, if it's your eye, right? If it would have hit that cell of the retina, we sum all of the photons that would have hit it, and that's what we get. And furthermore, these photons, they have a wavelength, right? A photon is a thing that sort of oscillates, and that's the color, right? So by tracking the color of those photons, we would also know what color that pixel should be by summing up all of those wavelengths, right? Now, obviously, if you haven't gotten the sense already, this is just the idealized model of the lighting process. Nobody actually does this. Why don't they do this? Because even the most basic scene with like one light in it is billions and billions of photons, and there's no way to simulate billions and billions of photons in a 60th of a second. So for a game, it's totally unacceptable. Even for offline rendering, it's usually too slow to do that. So what we typically try to do with lighting is we try to do one of two things. In the pre-rendered world, we try to come up with essentially ways of sampling this process. So if you're Pixar, right, or your Next Limit, and you make Maxwell, the renderer for architecture and stuff, or whatever. So you can take a long time and lots of computing power to produce an image. What you typically do with lighting is you try to come up with ways of sampling this process in ways that do not have to simulate all billion, trillion, quadrillion, madzillion photons to get a good result, right? And so they do things like Metropolis light transport and bidirectional path tracing and blah, 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 which are all these sort of ways of saying we have this tremendous number of photon paths in the world. We have no way of simulating them all. How do we sort of go about picking which ones might be relevant to simulate and approximating from those what the rest of the lighting should look like, right? So again, you can kind of imagine, I don't want to go into too much detail because they're not relevant here, but you can kind of imagine how these techniques work, because if you think about it, there's, first of all, a ton of photons never hit the eye, right? If you think about the photons, look around your room. If you think about all the photons that are bouncing around your room right now, most of them don't go into your eye. So for starters, typically what you do is you trace outward from the eye, right, to look for lights as if the photons were traveling backwards, right? So just from there, that first initial transform is a good way of starting to say, let's cut out a bunch of photons we don't care about. Furthermore, when you start to look at surfaces and stuff, you can say, well, I know this surface has certain reflectance properties, so I know that photons that come in, about here almost always get absorbed, and photons that come in here always bounce out that way. So if I'm looking at it this way, I know I don't have to look in this direction, and I know I don't have to look in this direction, roughly, because those photons almost could never bounce out to the eye from that point. So I can concentrate my search in like this direction, right? So you do a bunch of stuff based on probabilities, essentially, to start to try and reconstruct what it is. And there's some really fascinating work in this direction. Specifically, the sort of the chain of work that started by Eric Veitch when he wrote Metropolis Light Transport, and everything that followed thereafter is really interesting. a lot of it has to do with basically saying we can reduce the number of samples we need to take and the number of paths we need to compute rather dramatically just by looking at this problem as a probabilistic problem and focusing, understanding how to take samples in the places they are most useful and how to weight them properly to produce results that on average produce the correct result as quickly as possible, right? So, the offline world does things that way, and the reason for that is, again, they're trying to produce very realistic results, and they can spend 12 hours a frame doing so if they want to, right? Not so for Handmade Hero. Handmade Hero isn't even supposed to require a super high-end graphics card to run. It's a 2D game, so we don't even have the geometry we would need to do a lot of the stuff that we're talking about there. We would have to approximate it. So we're not trying to do that. What we're trying to do is we're trying to come up with something that will be artistically pleasing, right? We basically are trying to come up with something that has to do with light that will be reasonable, that will make you feel like there is some lighting without costing a huge amount of computation. Now, let's talk about some properties of light that have an effect here. So, first of all, let's talk about the concept of fall off. Now, one of the myths of light that a lot of people intuitively think, but it's not actually true, is that light gets dimmer as it gets further away, right? And we'll talk about why that is in a second. And in fact, it actually will for certain things that we are interested in. So I don't mean to tell you that it doesn't at all, but it's important to understand that that's actually kind of a wrong way to think about light. It's more of a property of the integration of light, and we'll see that in a second. So let's talk about that. Let's talk about some of the properties of these protons that we care about. So let's say that there is a distant light source, right? Let's say that there is a street lamp, maybe, right? So let's say I've got like a street lamp here. And I am looking at the street lamp. The street lamp is lit up by a light bulb. I am seeing a photon that comes out and it hits my eye, right? And furthermore, let's say that I have walked backwards and there's a photon that comes back and hits my eye here. The crucial thing to start your understanding of light with is that that photon does not get dimmer as it travels further away. Photons do not dim along a line. When a photon comes out of a light source and travels a mile and hits your eye, it is as bright as if you were standing with your eye right up next to the light. There is no difference in the photon's perceived brightness to your eye. Okay? So this is crucial. Light does not diminish along a line, ever, under any circumstances that I know of, period. Now, again, I'm not a quantum physicist, so maybe if you were a quantum physicist, you'd be like, yes, it does. If you go many millennia, light years away, and you're talking about the relativistic spin of the blah, 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 right? So, I don't know, maybe there is some way for a photon to somehow be dimmer or brighter in relativistic terms or something. I have no idea. Like the energy that it has will shift. And that would seem logical because, the wavelength of a light. But again, in terms of brightness, there's the wavelength of the light is its color. It's not its brightness, right? Its energy is its color, not its brightness. And so, what do I mean when I say this? And why do things look brighter and dimmer? Well, the thing to remember is What's happening when you see a brightness is you are seeing the amount of photons that hit your eye, right? It's effectively a count. So when you look at something and say, is it brighter or dimmer? What you're actually asking is how many photons have hit your eye from this light source, okay? So a single beam of light, a photon that goes out of a light source and hits your eye, can never get stronger or weaker for that individual photon. So when a light looks brighter or dimmer to you, the only thing that can be happening there is less photons or more photons are hitting your eye from that light source. That's the only thing that can change your perceived brightness of that light source. The photon itself that goes along the line doesn't get weaker as it comes to you. Okay? Again, really important to understand that. So, now let's take it one step forward. So, given that brightness is the count of photons, if I were to ask how many photons would be hitting my eye at these two distances, right? If I were to ask how many, I would be able to ascertain the brightness. So let's ask that question. How many photons, proportionally speaking, will hit my eye at, say, 1 mile away, right, versus 2 miles away? It's a legitimate question, right? Well, it's a little difficult to answer without thinking a little bit more about how this is emitting photons. If this were a laser, meaning it's a highly correlated stream of light where all the photons are shot in a very specific direction, the answer is probably roughly the same number, right? Because remember, photons do not diminish along a line, and if I was shooting all of those photons out directly in a line, then they would just all hit my eye in both cases, right? And yeah, lasers aren't perfect, so eventually I'd get far enough away that maybe that wouldn't be true. But for the vast majority of that relevant distance, it would just, all the photons would hit, right? So let's talk about something that's not a laser, since lasers are usually not what we care about, right? A laser pointer is not the thing that we're lighting most of our scenes with. So what does a light like a street lamp do? Well, what it does is it's outputting a certain number of photons per second, right? But it's outputting them in every which way, right? So if I were to take what angle my eye can see, right, I've got a very different setup than a laser. So let's take a look at what that looks like. Here's my light bulb. Here's my light bulb, and here is my eye. Now, we know the eye is a lens, so it's going to focus a cone of light onto a point, right? A particular retinal cell in the back, let's say here's that cell. We're talking about that particular retinal cell, so one point of your vision. Well, this lens is going to focus basically and we'll say this is a point light source for now. It's really, well, I don't even have to. So it's a spherical light source. So it's going to take all of the light that can be shot in this direction, right? And it's going to focus it like that. So it's effectively, it's not really a cone. It would be a cone if we were talking about a point light source, right? It would be a cone. It would like a cone that maps down to a point via the lens. This is the eye lens, right? But we're, even if the light source has some area to it, we're still talking about a cone that's just kind of a little fatter at the end. And inside this cone, right, it's shooting out all these photons in this direction. And all of those photons that are shot out in that direction, they will come and hit this lens and be focused onto the eye, right? That's what a lens does. That's why you use a lens, by the way. The idea behind a lens is to take a cone of light instead of a point of light. Right? It helps you get a brighter image when you're looking at something, as an aside. All right. So what does this mean? Well, this lens from our eye, it does not get bigger when we get further away, right? So if we were to take what would happen if I was to put the lens back here further, it's still the same size, right? So what ends up happening is, let's say, for sake of argument, this is a very weak light source, so it's not emitting very many photons per second. And let's say that there's only a few that will actually hit. There's only 3 that it emitted that will actually hit the lens. And here they are. Okay? So those photons hit the lens, they focus onto this point, right? And that's how much energy I perceive, how much brightness I perceive. I perceive 3 photons. Well, now if I go back really far, what happens now? Well, if we continue these lines, you will see they miss the lens. Right? So only 1 photon will now be focused, right? Only 1 photon will now be focused onto my retinal cell. So as you move a lens further away from a light source, it absolutely collects less photons from an emitter, right? That is 100% true. And this is before talking about any of the other things we need to talk about, like participating media, haze, that sort of thing, right? So you can see very clearly from this diagram, as I move further away, I collect less photons. But, and so now you're going to say, well, okay, Casey, you just told me that the light, well, not I just told me, but, so now based on what you told me, Casey, I'm going to go ahead and say that, all right, so lights look dimmer when I get further away, right? Because they collect less photons. Not so fast. So, given that this is the case, you now have to think about this in 3 dimensions. What does this actually look like, right? Well, a light source is therefore emitting, right? And a lens is therefore collecting stuff effectively as an area, right? If I took a solid angle, right, that I said, okay, how much photons are emitted there? They hit this lens and they focus, down onto a point. Everything in that assembly is an area. We're measuring an area of photons that are emitted, right? A solid angle, it's like a bundle, it's a surface area of photons that are coming out and then hitting the lens and then bouncing back, right? That area, as it gets further from the light source, right, gets bigger and bigger proportional to the distance. So if I were to look at it again from the side, as I emit outwards, right, what I'm going to end up doing is, as I get further away, the spread of those photons is going to increase with the distance, proportional again to this triangle, right? It's good. The size of this, effectively, right? The size of that area is going to be exactly proportional to the distance, right? Whatever the distance is, as this distance goes up, so too will this. It's a similar triangles relationship, just like the projection equation, right? And we know that, this is just going to be proportional to the cosine, effectively, of the hypotenuse, right? Which is proportional to distance, right? And these two are proportional to each other as well, right? So basically, the area is going to be proportional to the distance. But remember, there's 2 dimensions, right? We're talking about area squared. So the same amount of photons, as I get further away, is going to fall on an area that's a square of the distance. And this gives rise to what's called the inverse square law, right? Why is it called the inverse square law, and what does it mean? Well, the inverse square law says that light essentially diminishes with the square of the distance it travels, right? And the reason for that is not because the photons get any less bright. It's because the photons are spread over an increasingly wide area. So the chance that you will get something will get hit with a photon is 1 over the distance squared, right? Why? Because as the distance increases, A increases, and we know if this is the side here. I shouldn't say A because A sounds like area. I don't know why I picked that. Let's just say that's width or something, right? So there's width. So it's, the area equals the width squared here in this case, right? Because it's a square. And since width is proportional to distance, what that means is 1 over the distance squared is the chance that a particular photon will hit you as you get further away. If you're right at the light source, obviously it'll always hit you. As you get further away, it diminishes with the distance squared, right? Make sense? Okay. So now you ask me, well, okay, so if that's the case, then surely what happens is, as I get further away from a light source, as I'm walking further away from a light source, it's going to look, if I were to draw its brightness curve, and a distance, it's going to look like that, right? It's going to look like an inverse squared curve or something. It's going to look like 1 over 1 over a square. Nope. That, unfortunately, is taking much too simplistic a view of what's happening here. Yes, this is 100% correct. And yes, as I get further away, the number of photons that are going to be hitting my eye is exactly proportional to this. But, and I should mention, the actual brightness of the light is actually diminished to 1 over d squared. It's actually happening. But that is not what you will say. And you can prove this to yourself right now if you want to. Take a light source in your room, whatever your lamp is, and look at it and walk away from it. Does it look like it's getting any dimmer? It should. 1 over d squared is a very steep fall-off curve, right? It should be looking crazy amounts dimmer as you walk away from right up close to it to further away. But it doesn't look any dimmer, does it? Right? So the question is why? The answer is because that is not what we're actually talking about when we talk about how humans perceive brightness. Humans do not perceive brightness by saying how much light from this light source fell on my eye. If they did, it would look much dimmer to you. Because, hey, guess what? The light source went from being really big in your eye, which is very bright, to being very small in your eye, which is not very much light at all, right? But that's not how you think of brightness. What you think of brightness as is for the area of my eye that this light is taking up, how bright is it? And it just so happens that the projection equation is the inverse of the photon spread equation, right? My light source over here that's shooting out these photons, right? They are getting smaller at 1 over d squared, right? But my projection equation is doing the exact opposite to the light source as I get further away, right? It's shrinking it down. So the size of the light source is going to be 1 over this distance squared, right? So effectively you have 2 d squareds canceling each other out. Yes, I have 1 over d squared the number of photons, but they're taking up 1 over d squared the amount of space on my eye. So they still look exactly as bright because I have that many fewer cells receiving them, right? So here we get to the first weird part about lights, which is that direct lighting, right, direct view of a light is constant from any reasonable distance. Okay? I don't care how far away from this light you walk. The only way you can make it look any dimmer to you if you were in a vacuum, right, in space, is to get so far away from it that your retina cells are no longer at a sufficient resolution to pick up the photons. Then it'll start looking dimmer. But until then, it will look the exact same brightness. And the reason for that is the projection of the size of the light onto your eye is exactly the inverse equation of the photon projection equation that's spreading out the photons. So they perfectly cancel. Just as less photons hit your eye, you are trying to collect them with less cells, so the apparent brightness is exactly the same, right? Okay, So now, let's talk about the next thing that can happen. In the real world, photons do not make it all the way to your eye. Here is my light source again. And here is my eye. Photons launch out from the light source. They're trying to get to the eye, but what happens? Oops, it's something in the air. Dust. Sad. Sad for the photon, right? And what happens is the photon hits the dust and is scattered in some direction, right? Now, photons that would have hit the eye cannot make it to the eye. So some of them hit, right, that happen to avoid the dust, some of them don't. And there's dust all throughout here, right? This is called participating media. And it basically means that in most real-world scenarios, since the air, even the atmosphere itself, has water droplets in it and things like this can reflect light, in a lot of circumstances when we're talking about the lighting of things, we can't even really take it as literally as I just said, because even though it should be the case that lights do not diminish along a distance, in the real world they actually will. And the reason that they will is because things, dust, particles, air molecules that reflect the light are in the way. And that will affect your perception of the brightness. And this is why if you get far enough away from the light source or you look at it in a dusty room, it will change the appearance of that light source. Now, one thing to keep in mind is this doesn't necessarily mean things will get dimmer. Sometimes it may mean that things will get brighter. And the reason that they may get brighter is because you have to remember light is coming from everywhere and can bounce in all sorts of directions. It may be that the participating media actually makes it easier to see. So for example, let's say I took dense smoke, right? So like something's on fire. This is participating media that will make light look dimmer. When I try to look at a light on the other side of the smoke, it will look dimmer, or it may black it out entirely if the smoke is very thick. That is because that smoke is absorbing the light. It doesn't reflect very much light, so you don't get much in the way of scattering that you can use to collect some of that light source. It's basically just absorbing it and getting rid of it. On the other hand, you may see on a hazy day, right? Yes, I look out and I can't see the mountains in the distance, but it's very bright back there. Why is it bright? Well, it's because all of this light is coming in from elsewhere, getting scattered toward me, that normally wouldn't. So it may actually be much brighter in that direction than it should have been. The light from behind the mountains were actually kind of dark colored. I shouldn't have seen very much. Instead, I see much brighter. And that's because all of the sky incoming light and the sun and everything else is getting scattered back towards me in ways it wouldn't otherwise have, right? So again, participating media really changes things up, and you have to sort of start thinking about the properties of the particles and how many there are, how dense they are, what kind of scattering they're doing, where the light's coming from. That's a much more complicated situation, right? But again, relative to the relevant to your understanding of light, because participating media will do that. Okay, so finally let's talk about the last bit of the problem, which is the part that we care probably most about in Handmade Hero, and that is reflection. So basically, most light we see is reflected light. Typically, we're not staring directly at something that's emitting photons, right? That's uncommon. And in fact, you might even say that typically when you're looking at a light bulb, even that's not really looking at something that's emitting photons, because the photons that are coming out of that light bulb are actually hitting a coated surface that diffuses them more than they would normally be diffused, right? Typically, we don't look directly at the filament of a light bulb, unless you've got artisanal light bulbs, which are increasingly common in places like Seattle, but separate issue. All right, anyway, so in this case, what we're really concerned most about when we talk about how things look is how light is reflected, how it's reflected off objects, how it's reflected off coatings on things, that, like even if it's translucent. That's what determines most of what we see, because most of what we see isn't emitters, it's reflectors. Yeah. Now, I guess I should caveat that by saying, well, maybe that's not true anymore because a lot of times we look at computer screens all day, and computer screens are sort of emitters of light source, so maybe that's not exactly right. But, oops. Looking at the real world that doesn't have a computer screen on it, it holds. Okay, so how does reflection work? Well, reflection just works by saying, all right, I've got a light source, right? And I've got an eye. And what happens is photons get shot out that wouldn't normally hit the light source, right? Here's my object. So normally this eye wouldn't see them because they're going to go this way, right? And it's not going to see those photons. Maybe there are some photons that do shoot out, right, that will hit the eye directly, but there's a bunch that won't. However, some of these photons go down and hit this object, and they get reflected back in a provident direction that happens to also hit the eye, right, the lens of the eye. And so that is how we see most things that we see, is a photon has launched off of a light source, it's hit an object, and then it's bounced into our eye. That's how we even know the object's there at all, right? It's basically a flood of photons that's bouncing off of things, and we're seeing the bounces, right? And you can even see this for yourself if you've never done this. If you're in a very dark room that drops below the sampling integration ability of your eye to smooth out, in a very dark room, you can actually see it like very noisy. It's very, very noisy, right? And the reason for that is you're just not getting enough photons bouncing off things for your eye to actually come up with a solid estimate of what the lighting is in that direction, right? So it's varying wildly second to second as different numbers of photons hit your eye from the same direction. Normally, when you have lots of light, that noise level of photons, because remember, photons are randomly spewing out all over the place, right? So you're not getting a constant number of photons hitting your eye every second. You're getting a very variable number, but that number variance is so small compared to the magnitude. So if you looked at it, right, of brightness, right, over time, you're getting something like, like this. So there's this tiny wobble, but the amount is so huge compared to the wobble that your eye has no trouble just filtering it and going, here's a constant color, and so it doesn't look noisy. But when you're way down here and you get that same wobble, you're going to magnify that part of the graph, and here's what we're looking at now. Well, all of a sudden it looks like this, right? Because remember, your eye is adaptive, and when things get darker, right, it dilates the pupil to collect more light, and your brain is trying to scale up the amount it uses for a particular level of brightness so you can see. Now, relative to the number of photons hitting your eye, right, the noise is really relevant. It's drastically changing the number of apparent photons hitting your eye, right? So again, random photons just spewing out into the world, hitting things, bouncing off, hitting our eyes, that's how we see. So now we have to ask the question, well, how does all that stuff we just talked about, how does that affect light that hits the surface of an object, right? Because that's what we have in Handmade Hero. We've got all these objects. They're not emitting light. They're just reflecting light. How do we think about their illumination properly? Well, when things hit an object, what happens is that same inverse square law applies, right? So however many photons came out of this light source, when they hit this object, right, as the object gets further away from the light source, the inverse square number of photons will be hitting its surface, right? So the strength of a light source, again, diminishes with 1 over the square of the distance traveled to reach the object. That's the number of photons that will hit it. So the number of photons that are reflected off of it is again proportional to 1 over the distance squared of the object, right? Now keep in mind, again, it does not do 1 over the distance squared to the eye for the same reason. As this object gets further away from the eye, it takes up less space in the eye, so the apparent brightness is, again, you're concentrating those photons on smaller numbers of cells. So the distance between the light and the object changes its brightness because less photons can be bounced off of it. But the distance back to the eye from the object, not relevant. Does not affect the brightness, right? Very critical to understand and very strange, right? When you don't, it doesn't make quite intuitive sense at first. Okay. So for our purposes, there is an inverse square fall-off on lighting if we want to be accurate. Now remember, accuracy is not our goal in Handmade Hero. It's just good to know what would be correct when we go to do things. But that doesn't mean we will want an inverse squared fall-off. It doesn't mean that we have to even do things like take into account the distance from the light source objects. We can do whatever we want, right, as long as it looks good. But it helps to understand how light works, so you can at least start there and work backwards to something that looks like what you want, rather than going, I have no idea, I'll just start making up equations, and then they don't really look at all like light, and you're kind of confused. So it's good to just understand what is going on there. So that is how light bounces off a surface, and what's worth noting about surfaces is how they distribute light makes a big difference as to how that light will be perceived. Why is that the case? Well, let's talk a little bit about reflectance functions, and hopefully we can see why we care about that. Right? So here's the surface of an object. Here's my light source, and here's my eye. I'm going to look down at it. So let's say I look at this surface here. Right? And again, here's my lens. So I'm going to look down at this point on the surface. And you can see that, that lens is going to collect everything in a cone. So from this particular point on the object, I'm actually getting everything that bounced off in sort of like, again, a conical sort of outpouring there, if you will. So if we want to know what the brightness of this surface would be at this point, what we basically are asking is, for any photons that could come into this surface from any light sources from anywhere, how many of them would bounce out along this cone? Right? That's the brightness. And if we care about things like the color and that sort of stuff, we would also want to ask, how did those photons change their color? Like, what color were they when they came in? How does the wavelength shift when it hits this object? Blah, blah, blah. Right? But for right now, let's not care about that. We're just going to talk about the brightness. Well, the answer is surfaces each have sort of a molecular structure, if you will, at their surface boundary that determines what will happen. So you have to imagine the surface isn't flat, no matter what it is. It's actually like a bunch of molecules bouncing around, right, that are all held together in like a lattice form or something like this if it's a solid object. And what happens when a photon comes in is it's going to strike these things and bounce out, right? If it's not absorbed. So it's going to bounce these things and it's going to shoot out, right? And by the way, I shouldn't use the word absorbed. I've been using it this whole time because in the graphics world, we think of it as absorption because it's absorbing light, but really it's probably not absorbing light per se. It's going to go into heat energy, or there's the actual molecular activity of it is not our concern. When I say absorb, I don't mean to say that it captures the photon in some specific way that's quantum dynamic and all this other sort of stuff. I don't care about that, and I don't know about that. All I'm trying to say is the light gets absorbed from a lighting perspective. It will not bounce out. But what actually happens to it is a physicist's concern, not ours. Maybe it sort of knocks a thing around and transfers its energy and goes away, or maybe it gets captured in some way and released later, or in some other form like heat, energy, so it's converted to IR wavelength. I mean, who knows, right? The point is, from our perspective, when we say absorb, what we mean is a photon at a visible wavelength struck an object and it never came back. That's all we know. Whether it transferred into heat or something else, we don't know, we don't care. Or ultraviolet, not our responsibility. But we know that it didn't come back in the visible spectrum. And that's all we need to know for lighting. Okay, so what that means is that the microfacet geometry of the surface, what happens to it at a molecular level, what it looks like, changes how photons reflect on an angular basis. If the surface is completely fair and will reflect in a completely uniform way, which almost no surface is, but there are some that are quite close, then what will happen is a photon that comes in has an equal chance of being reflected out in any direction. This is called a perfectly diffuse surface. Basically, what it means is that it's a completely random collection of molecules on the surface as far as reflection is concerned. When you hit, you could go in any direction completely randomly, right? That is not the common case. Most surfaces are not perfectly diffuse. What is more likely is the microfacet geometry, and let me draw something for you there. What that means is that for an incident photon, the lobe, right, coming in at this direction is perfectly uniform. It could go out in every direction, right? So a photon comes out in here, it has an equal chance of going out in every possible direction from the surface, right? That is not the common case. The common case is that it's biased. So the light comes in, right? And yeah, it may come out in a lot of directions, but it's actually strongly sort of biased in the direction that's a perfect reflection or something, or maybe not a perfect reflection, but so it could backscatter, and often does, but it more often goes out in these other directions, right? So it's more likely. And the way you draw these lobes, right, is these lobes that people draw are just ways of saying, oh, here's sort of the distribution. It's basically like taking a graph of percentage chance the photon will go off in a direction and wrapping it around the angles that it will go out, right? So if the lobe is further out in this direction, it means there's a higher chance. If it's closer in, there's a lesser chance, right? Now remember, this is a completely four-dimensional function. The angle that you go out at is determined by the angle you come in at, and of course it's 3 dimensions, so there's 2 angles, right? So we have to think about this for every possible incident angle. You can see why this is a pretty complicated function. These are 4D functions at a minimum. They're actually worse than that in the real world, because if you think about what actually happens, 4D is only for point reflectors. And really what happens in the real world is most surfaces do not bounce things off directly from their surface. Most of them have some depth. The photon comes in, it travels around, and then comes back out later. What that means is that the point of impact is also a parameter. So it's really 6D. It's the 2D parameter on the surface where the light came in, and then where it bounces out, right? So it's pretty nasty. And really this might not even be the right way to think about it. Point being, it's worse than 4D, because you basically have scattering that happens inside the surface. So typically, I think if you try to do this really accurately, you don't try to wrap it up in one function. What you do is you have a penetration function that basically says, when I hit the surface of this, what direction do I go in, right? And that's a probability. Then when I go in, I actually simulate bouncing around in here. So I do several bounces interior till I strike the surface again. When I strike the surface again, I have a function that says what direction I emanate, and then I go out. And that's the full simulation. Heaven help you, right? So anyway, there you go. So all that lighting stuff, again, worth knowing. And we covered this. We did some lighting way back on Handmade Hero, but it's been so long ago. I just wanted to refresh everything. That is the basics of lighting. Hopefully everything is paged back in for you here. But that is essentially how to think about the light as it travels around the world. Now, there's some more complicated stuff that goes on in here as well that has to do with cosine fall-off. There's sort of this concept that as I think about lighting that falls onto a surface, if it's coming down straight versus it's coming down at an angle, the shaft of light is truncated based on the cosine of the angle that it's coming down at, which is, again, not something I think we'll end up having to deal with in Handmade Hero, but it's another microfacet element that affects if you're trying to produce accurate lighting equations. it's something to be aware of. And basically all that is saying, well, you can imagine if I've got photons coming down at a surface and they're coming directly down at the surface, then the whole surface, the whole sort of amount of photons hitting will bounce back. The width of this is on the bounce is exactly what it is on the incidence, right? But on the other hand, if I take that and I shoot it at it this way, right? What you can see, oops, hopefully here. What you can see is the same number of photons coming in at this angle, spread out on, unfortunately, a much wider angle, right? So what ends up happening is that this area here, the hypotenuse here, right? The cosine of that hypothesis, that's good, hypothesis, of that hypotenuse is actually the amount of light that is incoming there, right? And the same would be true for reflection. So when it's going out at an angle, you have a cosine, whatever the surface area patch you're working with, you have a cosine term that says how big the outgoing shaft is by comparison to how much it was on the surface. So at a micro level, what this leads to is you end up having a lot of cosine terms in your lighting equations if you're trying to simulate them correctly, because you have to model the fact that the light falling onto a surface and then getting bounced back out is undergoing this cutoff for a particular pixel, however much the element size is that you're trying to simulate on that sample. All right. So all of that stuff is, again, not something we're really concerned with on Handmade here. I just want to make sure you've got the basics. Again, I think we covered it. Does anyone know what day we covered it on? Miblo says day 96 or 97. So day 96 or 97 back there somewhere. There's another set of this. Hopefully between the two of those, I've hopefully gotten everything that you need to know on that out there. Sometimes I forget things, so I don't know. Hopefully it's the case. But now let's talk about what we might want to do on Handmade Hero. So on Handmade Hero, we have a couple of choices, right? But basically, the main thing we care about with our light is we're going to have in our world, right? We're going to have some light sources, like maybe there's a campfire or something like this. Probably not a campfire, but let's say there was. There's a campfire or something, and we want the player to see sort of some shading, some lighting happening in the region of the campfire. Now, there's two ways that we can do this, right? The most straightforward, simple, artistic way to do it is to literally just have the brightness occur within radii or something like this. And so it's basically sort of like almost like a sphere that you splat down that just makes things brighter. And you see this in a lot of games, especially if they're sprite games, because it's harder to do much better in sprite games. But let's see here. So here's Stardew Valley at night. And what you can see in Stardew Valley at night is here's two torches and another. Let me make that full screen there. Well, I guess I don't need a Stardew Valley review. I just want to view the image. Thank you. So here's Stardew Valley at night, right? And again, this is, it's a XNA game, I think, if I'm not very much mistaken. It doesn't have really any concept of what's going on in 3D, so it has to do something to give you the sense of lighting at nighttime. So what is it going to do? And what you can see here is all they do is they just take a region around the light and they color that region, and any region that is not around the light is darker, right? It darkens. And this is pretty effective, right? It works and it doesn't require anything special. Now, it has obvious problems with it in terms of what you might want as a nice effect, And what you can see is there's clearly reflections painted into the bitmap art of the light. You can see that the light is brighter here, for example. And that is completely wrong. So you can see that this light, like this is the light source right here. The reflection is as if the light was coming from here, which is completely wrong. Here's the closest light here. The reflection is coming from up here. There isn't even a light coming from up there, right? So it's, well, I guess maybe the moonlight, but you know, that's much weaker than this. So you can kind of see that like it's completely wrong. Like objects don't respond to the light correctly at all. And if the player was trying to use the light sources as a way of determining the shapes of these objects, it would completely fail, right? But fortunately, that's not what humans do. Humans understand approximations like this, so this works just fine. And they understand that this is a rock shape because it's representatively shaded this way, even though that's not the way it would have been shaded. And yeah, it doesn't add to the sense of atmosphere and lighting, so you get less of an effect that it doesn't respond in the right way, but it still works just fine. And so something like that is probably more of what we'll have to do on Handmade Hero, because again, we don't have 3D geometry for most of our stuff. They're just sprites, so we don't really have a lot of information about how they would reflect. Again, I'll show you another picture here of the simplest case, right? And it's just, again, everywhere there's a light source, there's just sort of this splat of light there, and that's it. Now you can do something fancier than this, obviously. If you take a look at, say, stuff where you've got a where you have a normal map, and so what that involves is basically saying we've got a normal map on top of our sprites. Then what you can do is you can sort of relight the sprites to a certain degree, and you know, you can see what this looks like if you take a look at, say, something like Sprite Lamp, which is just a tool that people use for creating these. You can kind of see that you get, right, on a 2D surface, you can move the light around, and by using the normal map to relight it, you can kind of get something that sort of maybe looks like it's getting lit, sort of, right? Now the problem with this is just that it's not great. Like, you know, it maybe gives you a better sense, but whether it's artistically better or not is kind of hard to say, really. It's a personal preference, I guess is what I'd say. Sometimes it looks better, sometimes it looks worse. It probably depends. It's probably in the eye of the beholder, whether that's good or bad. And again, even that is only talking about inside particular sprites, getting some curvature information in there for the lighting, but it doesn't really even help with shadowing and stuff like that, because that's not really, you know, again, you still don't know, like when we run Handmade Hero, if we want to do some lighting, in here we have the problem of, well, what do we do to shadow things? If a light's on one side of somebody, how much shadow does it cast in the other direction? Blah, 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 blah. All right. So let's start with Stardew Valley style lighting, because it's the easiest possible lighting, right? The easiest possible lighting to do is we just have splats of light, and they're completely indiscriminate. So they just light things in a radius, right? So how would we do that? Well, we would start by saying we need a light direction, and I'll just hard code the light direction directly in the light position. I'll just hard code the light position in the shader, and then we can always just pass it down later, right? So let's go ahead and say that we've got the light in the shader, and that'll be, you know, a V3 light pause. And the light pause is going to be, let's just say it's at 0, 0, 0 for now. Unfortunately, I don't actually know where 0, 0, 0 actually is, but I guess we'll find out. And then we're going to need another thing, which is going to be, I guess, the light strength. Because we need some concept of how strong the light is, because if we're going to compute some kind of a fall off for our light, we need to know how strong it is to begin with, right? We need to know, we need to have some notion of how strong it is to begin with. So let's go ahead and say that we have a light strength. I'll set it to 1.0 for now, which again is unitless. We don't have any real, unless we actually go and try to simulate physical lighting, at which point we would be talking about lumens or something like this. We don't really have any way other than just sort of approximately saying we're going to come up with a brightness scheme for our game that's completely arbitrary, right? All right. So we have a light strength and a light pause that come in here. And then what we want to do is we want to have a way of taking the color values that we see and modulating them properly by whatever that light strength actually is. So the first step to that is finding out how far away the light is. And so what we want to do there is say, well, whatever our actual position in the real world is, we want to take the distance to the light source. And so in order to do that, we need to know our 3D position, and we don't really know our 3D position, right? All we get here is our fragment coordinate. So if you take a look at what we actually want to know here, we probably want to go ahead and add a thing here that's like smooth out v3 world pose or something like that, right? And so these invertices are coming in here, right? They're getting transformed by stuff. And that transform is a full transform that we don't actually want anything to do with at the moment, right? So what we want to do is we want to have some way of getting the world position in here. And we can assume, I think, since we don't use transforms to move things around, our vertex positions are actually in world space. I'm pretty sure that that's the case. I could be wrong about that. We'll have to go back and check. But I'm pretty sure that's the case. In fact, no, I know that's the case because the transform doesn't get set per thing. So if we were just to output the world position, all we really need to do here is say, okay, there's a world position. It just gets written out directly. So the world pose is just the input pose, right? It's just whatever we started with. And we just don't care about the W value, right? Now, since our trees use that Z bias thing, I guess really technically what we want to do is use the Z vertex version, now that I think about it, because we do want to account for the Z bias, I guess, because we want lighting to change as it gets higher. So really we want to use the Z vertex as XYZ. I think that's what we actually want. So that's our world position, and it comes out. We can then say we've got our smooth in, vec3, world pose, but now we know where in the world each pixel actually is supposed to be. And so we can figure out how far away it is, right? I don't remember if I have to do this computation myself, but I'm pretty sure it's actually built in. So I'm going to just double check that it is. Don't quote me on that. Oops, that's ES. I don't want ES. I don't want ES. I want GLSL spec. Where is it? Is this it? GLSSL. Oh, you know what? I want quick reference card. That's, sorry. I typed the wrong thing. That's what I wanted. All right. So here's all the geometric functions we have. And like I was saying, I believe, yeah, there is. I was going to say, I believe this is something I can just ask for directly, and I can't. Because, you know, we could just write it ourselves, but we want to use these built-ins when we can, usually because the graphics card is presumably going to insert the code that's most optimal for it. So there's distance right there. So I can just do the light distance is just distance, the world pose and the light pose, and that's it, right? Now I know how far away the light is, and I can use 1 over that to compute the distance. So all I should have to do there is say, well, okay, my light, the lighting value here is just going to be the light strength divided by the light distance squared, and that would be inverse fall off, right? And that's the lighting. So if I then want to darken everything, I can just multiply by that value, and I, in theory, should get a thing that lights in a sphere around this light. Don't know if I will or not, but in theory I should. Where is my error? Fix our compilers. Oh, I'm sorry. I didn't mean to say that. Oops, there we go. Didn't mean to put that there. It was complaining that there was a missing semicolon there. Didn't quite do it in the most clear terms, but that's what it was. So what you can see here is we've got our light source is centered at the origin, and it does exactly what you would expect, right? It lights things in a sphere around it, and it looks like a light, right? And like I was saying before, it's surprising how little your eye uses the reality of the cue. It's a completely incorrect light. I mean, this face that's facing directly at the light versus this face that's facing perpendicular to the light, they don't respond properly. This one should be much brighter. This one should be much darker because of the way most typical real-world reflection functions work. And yet, that is not at all what we get. Instead, what we get is something that the eye still interprets as a light emanating from that area, even though it's completely wrong, right? And this is why I say, it's worth understanding the basics of light, because then as you need more from them, you will know how to get that moreness, that more. But you typically will be very surprised at how forgiving the viewer is of complete incorrect results, as long as they have some basis in the properties of light. Gamers have been looking at wrong lighting for so long that they are very used to it, to say the least. So, that's obviously a very simple light source and a very simple way to add some lighting to the scene. Let's try making that be something that's a little more systemic. So what we could do, right, if you think about if we wanted more lights, we can add more lights, but it starts to get expensive, right? If we wanted to sum up the lighting in this area, you could imagine it would start to look kind of costly as we start to do this. If we created a second light, then we're doing more distance calculations, and we end up with this sort of thing. So here I'm going to create a brighter light, and I'm going to move it a little bit off to the side. It might not be far enough to the side. It's not. So there you've got two lights, right, that you can see. And the one in the center is not as bright as the one on the side, but they sum together properly in between them and stuff, and off we go. Now, we could do all our lighting this way if we wanted to. We could push all the lighting into the constant store, and off we would go. However, the question is that the most efficient way to do it? And it's a difficult question. It might be the most efficient way to do it. Certainly for a small number of light sources, it would be the most efficient way to do it. As that number of light sources get larger, though, it becomes too expensive potentially. And what we might want to do is pre-compute the lighting first into something like a voxel grid or something like this, and then just sample the lighting where we actually are in the world at that time, right? That tends to be the kind of thing that might be a little bit easier to do, because then it prevents us from having to have 20 light sources summed for every pixel we draw. So I don't know. So that, of course, is a tough question. because it is something that concerns how we're going to handle lighting in sort of a structural way. I'm not going to dive into that today. Maybe that's something we'll talk about a little more tomorrow. But what I want to talk about today now is, okay, so now that we know that we're going to compute some lighting this way, what else might we do here to improve the quality of the lighting a little bit? So the first thing we could do is we could start to take a look at sort of the facing direction of these surfaces in some way that would allow us to actually respond to the light differently depending on how we're facing, right? So, you know, I gotta be honest, I'm not sure. I mean, I guess for our cubes, it's easy to understand because our cubes are actually 3D geometry. So we can talk about how the light should really behave when it hits the cube. For our sprites, it's a little trickier, but I suppose still fine. For our sprites, since our sprites are facing only one direction in a sense, and by one direction I mean the band One Direction, you know, just absolutely fabulous. Some of the best music, really pinnacle of mankind's musical achievements. It's like, you know, it's like Mahler and then One Direction, but that's getting sort of off into a different situation. But anyway, so here, you know, I wondered I'm just looking at it, what should the lighting do on this? And I'm guessing, you know, we probably want something where we want to treat it as just a flat card, I guess, and say, well, if I'm on this side of the light source, I should be reflecting the light. If I'm on this side of the light source, I shouldn't, and my character should be darker, right? My character should be reflecting less light, I think. But either way, what this basically says is, in order to start treating this lighting a little bit more reasonably, what we need to do is have some way of taking that lighting and testing what direction what the facing direction of the surface is versus the light. And so what is that trying to simulate? Well, there's two separate things we're trying to simulate there. So let's take the first one. Here's my cube. Here's the eye. And here's the light. Actually, let's make the light a little higher. Okay. So, if we imagine hitting this surface here and the light hitting this surface here, what you can see is there's a reasonable reflection path for something that's facing, you know, this face of the cube, which is like sort of the Z face of the cube there, right? Whereas the face of the cube that's facing upwards, it's a really tough row to hoe, right? When the light source is so oblique to the cube like this, most of the light for a normal lighting function is going to reflect that light out this way. And very little of the light is going to backscatter on a typical surface like that. Very little of the light is going to backscatter back to the eye, right? So a perfect mirror, you know, if it was a perfect mirror surface, nothing comes back that way, basically. The only thing that comes back that way is stuff that comes in from over here, and there's no light out here. The light's coming from over here, right? For a perfect mirror. And as the surface gets more diffuse, it has to get up to an incredibly high level of diffusion before it's going to kick much light out this way. And even once it does, now we get into the cosine theta term problem here that we were talking about before, where it's like as this light shines in here and as it bounces out this way, the actual portion of a light shaft that can go out in that direction from something that hits is going to have the cosine term in there, right? Because what's going to happen here is, if we imagine the light shaft coming in, however much light is coming in, right, if we call this our L, that's going to get spread onto this big of a surface. And then the amount that's actually going to go out in that direction, same diagram, right? If we want to know, I guess let's say the outgoing reflection here, same difference, right? The amount of light that comes from a unit of the surface is going to go out proportional to the cosine of the angle to that surface, right? So that means as you get really oblique, this cosine term, right, as that angle gets steeper and steeper, the amount of light that can come out from there diminishes to basically zero, right, as you get perfectly down. So again, really kind of tricky there. There's just a lot at play. So what we would expect, though, again, is whatever lighting function we come up with here, it's probably going to take into account the angle there, and it's probably going to want to become dimmer as you get facing away from the light source, right? Or rather, you know, the surface, as the surface becomes that oblique to the light source, especially if the light source is on the other side of it. There is a weird property of light where if you happen to be going like this, where the light is perfectly on the other side, as you get to a really oblique angle, it tends to just graze off the surface, and most surfaces are actually really bright reflectors in this way. So if the light was over here, you'd actually get quite a bit of it. If you don't believe me on that one, you can do something weird. If you take a piece of paper and you look at a light source, really just glancing along the paper, what you can see is you get a very bright reflection. I don't know if I can really do it with this paper because it's all folded. But I'm going to look at the light source here. You get almost a mirror as you get to like the perfectly 90-degree angle. It's very, very bright along the paper, right? Whereas if I just bring the paper down a little bit, it's much darker. So like as you get to that perfect glancing angle, it's pretty darn good. It's almost, yeah, it's almost like the surface of water right there if you look at a piece of paper. So a lot of surfaces, they get very reflective right at that point where the light is just grazing off them. But again, we don't really care about that, so we can ignore that for now. So what we would have to do if we wanted to start taking into account angular issues is we need to start passing in what's called a surface normal. And a surface normal is just a fancy way of saying that we want to start passing in information about how the surfaces are facing, what direction they're facing, right? And so what we want to do is say, hey, this is a flat surface, it's facing that direction, right? This is a flat surface, it's facing that direction. So we just need something, a vector, that tells us what direction it's facing. So for every vertex we pass in, we can just pass in a vector that says this is the direction that the surface is facing, right? It's pretty easy to do. But it would require us, again, to sort of augment how we're doing things. Unfortunately, we've, I think, set ourselves up to make that not be particularly difficult, right? So if we were to take a look at our vertex here, textured vertex, if we wanted to, we can just add a normal vector in here, right? And that normal vector, just a three-dimensional vector, it just is going to say what direction the surface is pointing. It'd be pretty trivial for us to add that, right? There's nothing very difficult about that at all. So if I was to go find where we're writing these out, which is in our render group, what you can see is we've kind of nicely isolated everything down. The only place we do anything with it is in this push quad function here, right? And so what we would have to do is augment this push quad function to somehow figure out what these normals are, right? Now, we can actually just pass the normals down, and that may well be what we want to do eventually. But if we don't mind spending a little extra computational time here, we can actually produce normals without that in the first place, right? If we assume all our triangles are supposed to be coming from flat objects, which they are at the moment, right? Then what we know is if we're given 3 vertices, or in this case 4 vertices because it's a quad, then really we actually know, remember the cross product? Remember that guy? We have this idea that if you cross a vector A with a vector B, you'd get a vector perpendicular to it, right? Well, all we would have to do is pick 3 of these vertices, produce the 2 vectors, and cross them, and we would get the normal, right? That's all we would have to do, because the cross product gives us a perpendicular vector. If we want an arrow pointing out of our triangle, it's pretty easy to get. So what we could do is say, you know what? Let's just go ahead and produce the cross product of, 2 of these. Now we want this to be in the direction you can see the triangle, right? And remember, we were talking about the right-hand rule. So we know that if we have a triangle that's wound counterclockwise, which is how we wound our triangles, and we know that this is going to go like 0, 1, 2, for example, right? Then what we would want to do is make sure that we cross in this direction so that the normal comes out pointing us. Remember right-hand rule, curl your fingers from the vector A to the vector B, and your thumb is pointing out. If you use your right hand, your thumb is pointing out towards the direction the result of the cross product, right? So we want P1 minus P0 and P2 minus P0, right? Looking at that diagram. We want to do the cross of those two, and that will give us our normal. Now, of course, remember our normal is actually not quite right yet, because one of the things that we're going to want to do with this normal, probably since we're going to use it in lighting equations, we're going to need to do things like dot product and so on and so forth on it. So one of the reasons we want, when we're producing our surface normals, one of the reasons we often call them normals is because we want them to be normalized. So we want them to be unit length, right? So since we know that the cross product will actually produce something that's the length of A times the length of B, right? This is not going to be a normal. It's not going to be normalized. It's not going to be unit length. But we can just normalize it. Since we have that, we can do that like this, right? I forgot these are 4-dimensional. Oops. There we go. So that will actually produce a normal for us, and now that normal will be correct. And I can put it to do here. When we pass down the normal, there is sort of a caveat there, I guess, too, which is that when we do this subtraction, if we want to compute this correctly, that z-bias value that's in the w that gets added to the z, we should probably add it first, right? So probably what we want to do here is we want to do something a little bit more saucy, in a sense, right? We probably want to do something like this, which is like edge 1, 0 is this. And edge 2, 0 is this, right? So what we probably want to do here is when we do the subtract, we're going to get an additional z value out of it, right? So we probably want to do the z-bias here so that we will properly produce the normal for things that are for as if the things were actually there's biased z, right? Which I think this will do properly. I'd have to think about it. We'll check it a little bit more carefully later, but there you go. Right? So there's the surface normal, and now that's getting stored, right? So now we're writing out that surface normal, and we have it in our vertices. What that means is we can pop back to our OpenGL now, and we can say that that surface normal is something that we can handle in our common set. So what we can do here is, let's take a look at this. When we do use program begin, we can say there's now an n array, and there's a normal ID. And then we're just going to use that exactly like everything else. So we'll say our n array and that's really all there is to it, right? Oops, it's only 3 long. One of the things we want to do here with that normal is we want to, like I said, set it up. So we also got to take it down. Oops. So this will unset it. And then the other thing we got to do is when we actually get the uniform locations, let's see where that's happening. There it is. So it looks like, do we do this manually every time? Looks like we do. So why do we do that manually every time? Does anyone know why we do that manually every time? Like, why wouldn't we just do that in OpenGL create program? I feel like we just should. Right? I mean, doesn't that seem like the more reasonable thing to do? So in OpenGL create program, right, why don't we just do this? Like OpenGL create program, and then it takes one of these things here. And so then you don't return anything. You just say get all my stuff. I don't know why I didn't call that vert n. I probably should have. Vertnid. But that seems a lot saner to me. So I think I'm just going to do that. Okay, and then we've got our OpenGL create program here now, and I think we can just get rid of all of this stuff. So basically result common is now going to be written into directly, and this thing only has to get the stuff that's actually specific to it. What's the problem? Cannot convert from void to glue. Why isn't this wrapping anymore? That's weird. Cannot from void to gluent. Yes, that's correct. prog handle? Yeah. All right. So that's just cleaner, I think. And you know what? I could still return the prog handle as well, just to make things a little easier. There's no reason not to, I guess. So we can still return program ID. And this goes away. Gets rid of all that code. So now, in theory, we should have that array getting submitted. But in theory, unless I mess something up, and I obviously did, oh god. I was going to say it shouldn't do anything because nobody's looking for it yet, right? Or at least they should not be looking for it yet. I don't even want to know what just happened there because nothing should have happened there, right? Because we're not touching that array at all. So I'm not sure why it would be upset about it. Why, like, that should not have had any effect on anything, at least not that I could think of. Let me make sure I didn't mess something up in the create program. There we go. So the program handle is getting set properly. The attribute locations are in theory getting queried here and set. I'm going to step into use program begin just to see if anything looks weird. That all looks totally normal. So I have no idea why that's unhappy. It doesn't seem like it should be. I must have mistyped something somewhere. Because we always use textured vertex. Ah, right. That's the problem right there. One of those reasons I really do wish that C had a way of bulk initializing things more cleanly. Right? I would have liked that to have been able to say which one of these I was specifying, you know? Which I think they do in more modern versions now have. But anyway, this doesn't have normals, so we need to insert in here, let's see. Where's the other one? There it is. We need to insert in here space for the normals so that we can still set the other elements. There we go. Okay. So let's go ahead and go to the Q&A. We have prepared ourselves for tomorrow where we will have normals for doing a little bit more with our lighting. But let's go ahead and go to the Q&A for now. For the lighting of the sprites, do you need to compensate for the angle offset if it using the same light source as the terrain? I don't think I understand the question. We do, for the normals, right, we do want to take into account the fact that the sprites are sort of standing upright. And we are doing that by using the Z bias offset part of that in doing the normal calculation at the moment. So in theory, we are going to be taking that into account if that's what you mean. But if that's not what you mean, I'm not sure. Asaf Gartner says, there seems to be a lot of banding around the lights. Actually, no, that is not the Twitch encoding. There just is a lot of banding around the lights. And I don't know exactly what the banding is from. But I would assume, well, I don't know what I would assume. There's a couple different things that can be from, right? And I would guess some of it may have to do with the precision at which things are computed, because that can change, but I don't actually know. So it could actually just be because of the fact that we don't have enough color resolution. In theory, I would expect that to not be so banded, unless those are actually the... So here's one thing I will say. It is at least theoretically plausible to me that the internal precision of the buffer that we store back to is not sufficient, and so when we square and unsquare later, it's a problem. Let me just test something really quickly to see if that's the case. But the short answer is I'm not sure, since I haven't investigated it yet. I couldn't tell you what it is. So this right here, OpenGL default frame buffer texture format, in init we set it to RGB A8, and then if we allow, we set to sRGB alpha 8. So what we can do here, if we want to, is we could try setting this to an actual higher depth, right? So we could try some kind of a deeper frame buffer to see what happens to the banding. And I don't see any improvement to the banding there. So I mean, I would assume that it's some kind of a math precision problem, but I don't know. Where are these defined? There it is. All right. So we can set it to a full floating point frame buffer, which is, you know, in theory, way more than we could possibly need, and see if we still get the banding. But yeah, so I still see the banding there. So we've got some other problem, right? It's not that, which is, you know, I just wanted to double check. But yeah, I don't know what the banding's from. It's possible, I suppose. Let me also check just to make sure. I'll try to see what the actual pixel values are there. It may be that the banding is actually just unavoidable in terms of that's the color, that's the level of color you get in 8-bit. And in order to avoid it, we'd have to dither, right? Which we might want to do. But let's find out. So here's a boundary between two of them. So I'm taking this upper one here. Does that stay open while I do this? No, doesn't seem to actually work. So there's the upper one. It's 26, 40, 26. Here's the lower one. 25, 39, 25. So it's pretty much, that's as much as, that is the color resolution of 8-bit. Full stop, right? So the only way we could get rid of that banding, unfortunately, is to dither the output. Which, to be honest, I don't remember. Would you turn on dithering? We should have been able to, if we use a higher resolution back buffer, it should dither on display normally. So I'm not sure why it wasn't. That's not the dithering I'm talking about. So I just don't know. I don't know if this is the case or not. Like, I just don't know. So yeah, I don't know about this. Let me just see. I'll try turning this on. I'm gonna have to like spend more time finding out about exactly how we get it to dither the final frame buffer down. But assuming we set this to RGBA 16, so that our intermediate surfaces have more resolution than 8 bits, you should be able to get to dither on resolve. I don't actually know, though, what the correct way to do that is. I do not remember what the OpenGL magic sauce is to make that happen. I mean, we could implement it ourselves as well, too, which maybe we should do, but... So here is our final blit, right? It's right here. So right before we do this, where we're actually drawing to the final frame buffer, I can try just seeing if telling it to use Diffused there helps. I don't know that it will. Yeah, it doesn't. So we're going to have to look up, if we want to get rid of that banding, we're going to have to look up how to force it to dither. Let's see. Flying Solomon says, as our hero does not represent the actual hero that save our lives every day all over the world, I took the liberty and made some corrections to the game art. What? Okay, I'm going to skip that one. Stashio Cat. What kind of rendering pipeline does this use? Forward, deferred, or both? Well, it's forward, but it's a depth-peeled renderer, which is unusual. It's pretty bizarre. We may, in the future, want to do something with deferred, maybe, but probably not. I don't think we're going to need to. So it's forward with depth peeling at the moment. Graham7, is the debug text being lighted? Yes, at the moment it is. Use sampler with shift key pressed to get info window. Oh, in GIMP you mean? I'll have to do that. I missed the little line showing the current file name inside 4Coder. It was easier to file that way. Yeah, I don't use that anymore, but I could try to compile a special 4Coder custom for that. If you want to remind me, if someone wants to send me an email to remind me to do that, I'll do that. I'll build one on my other machine. ARF86, how expensive it will be if the light source is moving, for example, following the torch that hero could be carrying, or the flying light projectile? Well, right now, the lighting doesn't care where it is. So it's no more expensive to have it move than to have it be stationary, right? It's free to have it follow the hero around. Basically, all we do is change that value in the constant store, right? And then the light moves. So because we're not using any pre-computed lighting at the moment. OpenCoder update CodeXL. It will not be able to step into the shader, but you should be able to see the OpenGL state. I don't know. I think I'm going to uninstall CodeXL because it makes Visual Studio not work anymore. It will at least need to uninstall the Visual Studio part of it, I think. All right, so I think that's it. Stream has ended. I will be back here tomorrow for sure because we got more lighting to do, but for now I think we'll just call it. It'd be interesting, yeah, we'll have to take a look at what we can do about the banding. Oh, I forgot, right, since those lights are just absolute, they will, as we move down, as the world recenters, since we always render around the camera in terms of coordinates, as the world recenters, the light moves. That's cool. That's really cool. Awesome. All right, anyway. All right, so I'm going to wind it down. There we go. Thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can do your own experimentation with it. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot you can go to if you want to know when we're going to be live, and an episode guide for catching up on old episodes. That's it for today. I'll be back here tomorrow. I believe I said it would be noon tomorrow, noon Pacific Daylight Time. Until then, when we'll probably be doing just putting in the normal stuff, and maybe we'll take a look at that dithering as well, if we can figure out a good way to tell OpenGL to dither for us. That's about it. Until then, have fun programming, and I'll see you on the internet. Take it easy, everybody.